Something is shifting in the atmospheric systems that govern weather across the Northern Hemisphere, and the signals are visible simultaneously in multiple independent data streams that climate scientists and meteorologists use to assess what is coming. Not one indicator, not one anomalous reading from one monitoring station that could be explained as instrument error or local variation. Multiple independent systems, measured by different instruments using different methodologies in different geographic locations, all pointing in the same direction at the same time. When that kind of convergence appears in the atmospheric data, the people who spend their professional lives reading that data stop talking about normal seasonal variation and start talking about something larger, something that will be felt not in one region, but across continental scales. Something that the historical record of similar convergences says produces weather that people remember for years afterward. The jet stream is the starting point for understanding what is happening and what is coming. The jet stream is not a single river of air, but a system of fast moving air currents that circle the planet at altitudes between 5 and 9 miles above the surface, driven by the temperature difference between the cold polar regions and the warmer tropical and mid-latitude regions. This temperature difference is what creates the pressure gradient that drives the jet stream, and the strength and stability of that gradient determines whether the jet stream flows in a relatively straight west-to-east path, which produces stable, predictable weather patterns, or buckles into the deep north-south waves called Rossby waves that pull Arctic air far to the south and push warm tropical air far to the north, producing the kind of weather extremes that break records and make headlines. The jet stream is currently showing a configuration that atmospheric scientists describe as highly amplified, meaning the waves are deep, the north-south excursions are large, and the pattern is moving slowly enough that weather systems caught within it are persisting in place far longer than the typical timescales of mid-latitude weather. A slow-moving jet stream with deep amplification is the atmospheric configuration that produces the weather events that cause the most damage and the most disruption. Heat waves require a blocking pattern, a persistent ridge of high pressure that the slow jet stream maintains in place, allowing surface temperatures to build day after day without the relief that a moving weather system would bring. Flooding events require a persistent trough, a low-pressure system anchored by the same slow pattern, drawing moisture-laden air into a region and wringing it out repeatedly over the same geography, rather than moving through and allowing conditions to reset. The current jet stream configuration has both simultaneously in different geographic regions, which means that while some areas are experiencing or approaching heat extremes, others are dealing with flooding or persistent precipitation, that the atmospheric pattern is showing no sign of ending on the timescales that people in the affected areas are hoping for. The Arctic is where the explanation for what is happening to the jet stream begins, and the Arctic is undergoing a transformation whose pace and character have exceeded the projections that climate scientists were working with as recently as 10 years ago. The Arctic is warming at a rate approximately 4 times faster than the global average, a phenomenon called Arctic amplification that is the result of multiple reinforcing feedback mechanisms operating simultaneously. Sea ice reflects solar radiation back to space. When sea ice melts, the dark ocean surface, it absorbs solar radiation instead of reflecting it, warming the ocean, which melts more ice, which exposes more dark ocean surface, a feedback loop that is measurable, documented, and accelerating. The permafrost that underlies much of the Arctic land surface contains carbon that has been frozen for thousands of years. As the Arctic warms and the permafrost thaws, that carbon is released as methane and carbon dioxide, greenhouse gases that contribute to warming, which thaws more permafrost, which releases more carbon. Another reinforcing feedback operating in the same direction. The consequence of Arctic amplification for weather patterns across the Northern Hemisphere operates through the jet stream. The jet stream is driven by the temperature difference between the Arctic and the mid-latitudes. As the Arctic warms faster than the mid-latitudes, that temperature difference decreases. A smaller temperature difference means a weaker pressure gradient. A weaker pressure gradient means a weaker jet stream. A weaker jet stream is more susceptible to the large amplitude Rossby wave, configurations that produce extreme and persistent weather. The connection between a warming Arctic and more extreme weather events at mid-latitudes is a relationship that atmospheric scientists have been investigating for over a decade. And while the specific mechanisms and their relative importance continue to be refined through ongoing research, the observational record of the past 15 years is consistent with the prediction that a warming Arctic produces a more wavy, more amplified, more extreme weather-generating jet stream. The ocean temperature data adds another dimension to the picture of what is driving the current atmospheric configuration and what it means for the weather ahead. Sea surface temperatures across the North Atlantic are running at levels that have broken the historical record for this time of year by margins that the oceanographers who monitor these measurements describe as remarkable. The North Atlantic functions as a massive heat reservoir that exchanges energy with the atmosphere above it, and sea surface temperatures at the levels currently being recorded drive increased evaporation. Increased atmospheric water vapor and increased energy available to atmospheric systems that move over the warm water. Storms that develop over or move across anomalously warm ocean surfaces have more energy available to them. They intensify faster, they carry more moisture, they produce more precipitation when they make landfall. The hurricane season forecast, the predictions for atmospheric river events on the west coast of North America, the projections for severe precipitation events across northern Europe. All of them have been adjusted in response to the anomalous sea surface temperatures in the North Atlantic, and all of them point toward an elevated probability of the kind of high-impact weather events that make this season different from the recent historical norm. The El Niño and La Niña cycle, the periodic warming and cooling of sea surface temperatures in the equatorial Pacific that influences weather patterns across the entire globe, is in a phase transition that adds another layer of complexity to the current atmospheric situation. The strong El Niño that developed in the latter part of the previous year has been weakening, and the transition from El Niño conditions toward neutral or La Niña conditions is a period that atmospheric scientists have identified as particularly associated with disrupted and anomalous weather patterns. The transition is not instantaneous. The oceans release the heat they have stored over months, and the atmospheric teleconnections through which equatorial Pacific sea surface temperatures influence weather patterns in North America, Europe, Asia, and Australia take time to shift as the forcing changes. The result is a period during which the atmospheric patterns associated with the previous phase are breaking down without the new phase patterns having fully established, producing a kind of atmospheric instability that makes forecasting more difficult and weather more variable and extreme. The specific regional expressions of what is coming reflect the geography of the current atmospheric configuration, but share the common theme of deviation from historical norms in magnitudes that the historical record of similar atmospheric configurations suggests will be significant and in some cases severe. Across the central and eastern portions of North America, the deep trough in the jet stream that is currently positioned over the western part of the continent is associated with a pattern that draws cold, Arctic air southward while simultaneously funneling Gulf of Mexico moisture northward into the collision zone where the two air masses meet. This is the atmospheric configuration that produces severe weather outbreaks. The conditions under which the temperature and moisture contrasts between air masses are maximized. The atmospheric instability that results produces strong convective development. And the slow movement of the overall pattern means that the same geography is exposed to this setup repeatedly, rather than experiencing a single event followed by the pattern moving on. For Europe, the current atmospheric configuration is associated with a blocking pattern over the North Atlantic that has implications both for the temperature regime and for the distribution of storm tracks. Blocking patterns over the North Atlantic redirect the storms that would normally track across the ocean toward the British Isles and northern Europe, sending them instead either anomalously far north toward Scandinavia or deflecting them southward toward the Iberian Peninsula and the Mediterranean. This redistribution of the storm track has different implications for different regions. Parts of northern Europe experience drier and warmer conditions than normal, while the Mediterranean, which has been experiencing an increasingly persistent trend toward aridity driven by multiple factors, faces elevated flood risk from intense precipitation events when storms are deflected southward into the region. The Mediterranean flooding paradox, a region experiencing long-term drying, and water stress while simultaneously experiencing more frequent extreme precipitation events, is a consequence of the specific character of Mediterranean climate change, where reduced overall precipitation is accompanied by increased precipitation intensity in the events that do occur. The monsoon systems that govern the weather of South Asia and Southeast Asia, and that deliver the rainfall on which billions of people depend for agriculture and fresh water, are showing behavior in the current season that the regional meteorological services monitoring these systems are describing with concern. The South Asian monsoon, the seasonal reversal of atmospheric circulation that brings the rains to India and the surrounding region between June and September, is one of the most consequential weather systems on the planet, and its variability has enormous implications for food production, water availability, and economic activity across the world's most populous region. The current monsoon season is showing the kind of spatial and temporal unevenness that is consistent with the influence of the anomalous sea surface temperatures and jet stream configurations affecting the global atmospheric circulation. Some regions are receiving more rainfall than normal, earlier than the typical seasonal progression would produce, while others are experiencing dry anomalies that threaten crop yields and water supplies that the populations depending on them cannot easily compensate for. The wildfire risk implications of the current atmospheric pattern deserve specific attention because they reflect the way in which a changing weather regime interacts with the cumulative effects of previous seasons to produce compound hazards. Across the western portions of North America and across Australia, the combination of above normal temperatures, below normal precipitation, and the drying effects of prolonged periods of low humidity have produced fuel moisture conditions, a measure of how dry the vegetation that serves as wildfire fuel has become, that are at or approaching the levels associated with extreme fire behavior. Extreme fire behavior is the technical term for the fire conditions under which fires grow rapidly, resist suppression efforts, generate their own weather through the convective energy released by large fires, and produce the kind of catastrophic outcomes that have characterized the most destructive wildfire seasons of recent years. The atmospheric pattern that is producing temperature extremes in the affected regions is also suppressing the precipitation that would reduce fuel moisture, and the wind events associated with the jet stream configuration can drive fire spread at rates that overwhelm the defensive capacity of fire management agencies. The agricultural implications of what is coming extend the impact of the atmospheric changes beyond the immediate experience of weather into the economic and social consequences that flow from disrupted food production. The regions most exposed to the weather pattern shifts that the current atmospheric configuration pretends include major agricultural producing areas whose output influences food prices and food availability far beyond their immediate geographic boundaries. The wheat producing regions of the Northern Hemisphere, the corn and soybean belts of North America, the rice growing areas of South and Southeast Asia, all of them are experiencing or approaching weather conditions that agronomists and agricultural meteorologists are monitoring with elevated concern. The specific vulnerability of food systems to weather disruption is a function not just of the severity of individual weather events, but of their timing relative to crop development cycles. A heat event during pollination, a flood during harvest, a drought during grain filling, the specific timing of weather extremes relative to the stage of crop development determines whether the impact on yield is marginal or catastrophic. The infrastructure systems that modern civilization depends on, transportation networks, electrical grids, water supply and treatment systems, communications infrastructure, are all designed to the weather tolerances of the historical climate record. They are engineered to withstand the extremes that the past climate produced, with safety margins that reflect the historical probability of those extremes being exceeded. When the atmospheric configuration shifts in ways that produce weather beyond the historical range of variation, temperatures higher than the design tolerances of cooling systems, precipitation rates faster than the drainage capacity of flood control infrastructure, wind speeds above the structural limits of transmission towers. The infrastructure failures that result are not the consequence of inadequate engineering by historical standards. They are the consequence of a changed atmospheric reality that the historical standards did not need to account for. The preparation that is available to individuals and communities in the face of what the atmospheric data is showing depends on the specific character of the weather changes that are coming to specific regions, and the specificity of regional forecasting is where the science is most useful and most actionable. The large-scale atmospheric patterns that are shifting the overall character of weather across the Northern Hemisphere play out at regional scales in specific ways that depend on local geography, on the specific position of the large-scale features relative to populated areas, and on the timing of the pattern evolution relative to the seasonal cycle. Regional meteorological services are tracking these patterns with the best available tools and are issuing forecasts and warnings that carry the most current information about what specific regions should expect and on what timescales. What the data is showing at the broadest scale is a Northern Hemisphere summer atmospheric configuration that is loaded with the potential for weather extremes, for heat events that exceed recent historical records, for precipitation events that overwhelm infrastructure designed for the historical range of rainfall intensities, for severe weather outbreaks in the collision zones between air masses, for wildfire conditions in the regions where heat and drought have reduced fuel moisture to critical levels. The specific expression of these potentials in specific locations is the subject of ongoing forecasting that will sharpen as the atmospheric evolution continues. The broad pattern is clear. The detailed regional expression will emerge in the weeks ahead. The weather is about to change in a big way. The change is not uniform and it is not simple. It is not colder everywhere or wetter everywhere or stormier everywhere. It is more extreme in multiple directions simultaneously because the atmospheric configuration that is establishing itself is one in which the contrasts between different regions are amplified, in which the persistence of weather patterns is increased, and in which the energy available to weather systems is elevated by the ocean temperatures and atmospheric moisture content that months of anomalous warming have produced. The signals are there. The data is clear. The atmospheric scientists and meteorologists reading that data are not alarmed by individual readings. They are alarmed by the convergence, by the number of independent systems simultaneously pointing in the same direction toward the same conclusion. What is coming is significant. The question is not whether the weather will change. The question is whether the people and the infrastructure in its path are ready for the magnitude of the change that is already written in the atmospheric data for anyone with the tools to read it. The tools say it clearly. The atmosphere is loaded. The change is coming.